All right, this is the BC Calculus intro video for Power Series. And as we've been working on in section 9.7, we learned that we can use Taylor polynomials to approximate all kinds of functions, e to the x, cosine of x, sine of x, many, many others. And that not only can we approximate those functions with Taylor polynomials, we're going to look at in this section that if we continue that polynomial on, that we can exactly represent a function with a Taylor polynomial or a Taylor series, with the series just going on forever and ever and ever. We will generally call these series power series. And we're going to find that these power series look a lot like what we've been working with. For example, if we have a power series centered at x equals 0, that power series would look like this. I'm going to highlight these a values. Hopefully you can see that these a values would simply be a combination of coefficients and factorials and such that we would have had with the Taylor polynomials, right? And please also notice that this just continues on forever and ever and ever. And then, of course, for a power series centered somewhere other than 0, perhaps, like C, we would have this. So again, notice that this is exactly the same as the other one, and really this is just like those Taylor polynomials we constructed, and it does go on forever and ever and ever. So from here on out, we might talk about Taylor polynomials, Maclaurin polynomials, but we will heretofore reference these as power series and use that kind of language to talk about these. Let's talk a little bit about how effective these are at representing the functions that we want to represent. So we're going to find that not all power series converge for all the real numbers. We'll find one of three things to be true for a power series centered at C. So the first thing that is true, the first thing that could be true is that the series converges only at the centering point. We could also find that there is a limited radius. There exists some real number r, some positive number r, such that the series converges absolutely for this radius, right? That distance from the centering point. And then with some of them, many of the ones we've looked at, we're going to find that the series could converge absolutely for all x. We've already looked at some of those. And so these are the three possibilities. Either the series converges right at the centering point or converges absolutely for some particular radius, and also could be that series converges for all x. So as I mentioned, that the number r stands for the radius of convergence. If the series converges only at C, then the radius would be 0, right? We looked at this when we did our initial exploration into series. But if this is C, and maybe this is our function, and maybe the power series, no matter how many terms you have, only wants to converge right there at C. I missed. There we go. Then we would say that the radius of convergence would be 0. If, however, the radius of convergence maybe is some non-zero, maybe the radius of convergence, could be illustrated like this. Maybe my polynomial approximation, my series does that. Maybe you can see now that I've got this radius of convergence from there to there. Obviously not 0, but it's not for all real numbers. Or perhaps, certain cases, we could have a polynomial that will exactly represent the original function's curve for all values of x. Could be any one of those three possibilities. If the series does converge for all x, then we would say that the radius is infinite. Hopefully that makes sense as well. Converge for all real x. Let's see here. And then, of course, whatever that set of values for x for which the series converges is called the interval of convergence. So that would be like that blue marking that I made up here. From here to here would be the interval of convergence for that blue function. We'll get into all this terminology here as we get into these ideas with power series. Okay, the way that we decide the radius of convergence is by using the ratio test, just like we were doing in section 9.6. So a little review of that ratio test. The series we're working with converges absolutely if this limit of our ratio is less than 1. The series diverges if that limit of our ratio is bigger than 1, which also includes infinity. And the ratio test would be inconclusive if we do our limit of our ratio and we get 1. So the point here is that we are looking for a radius of convergence. And so as we're looking for the radius of convergence, we will be focusing on this first aspect of the ratio test. We'll be using this to help us find this radius and eventually interval as well of convergence. All right, so we're going to do an example here. This example asks us to find the radius of convergence for this particular series. And so as I mentioned earlier, we're going to use the ratio test to help us with this. So I'm going to set up my ratio. The limit is n heads towards infinity of, as you remember from before, it's the absolute value. And so because we're talking about the absolute value, the alternating element is not going to really matter for us here. And it's the absolute value of the n plus 1th term. So that's going to be n plus 1 times x plus 3 to the n plus 1 over 4 to the n plus 1. That's my nth term. And then that's divided by, or in this case, I'm going to do what we've done before. I'm going to multiply by the reciprocal of the nth term. So it's going to be 4 to the n over n times x plus 3 to the n. In order to find convergence here, we need this to be less than 1. All right, so that I can do my limit, I need to do a little bit of simplifying. It's going to be the limit as n approaches infinity of, well, let's see here. The n plus 1's not going anywhere. The x plus 3 to the n plus 1 would actually cancel with the x plus 3 to the n, so this would cancel with this. So I'd be left with just x plus 3. And let's see here. This 4 to the n would cancel with this 4 to the n, leaving me with just a 4. And then this n didn't go anywhere. Okay, so I think I've got everything handled there. Let me shorten this up a little bit. And I've got this still less than 1. Okay, so I'm ready to apply my limit. And let's remember that it's the limit as n goes towards infinity. It doesn't have anything to do with x. And so my limit as n goes towards infinity is going to apply just to this part. So you could use the pre-calc trick. You could use L'Hopital's rule. I would prefer the pre-calc trick. Notice the degree of the top and the bottom are the same. They're both n to the first. So I could apply this limit, and I would get 1/4 times x plus 3 is less than 1. All right, so then the absolute value of 1/4 is just going to be 1/4. I still have this x plus 3 in here. So to find my radius of convergence, all I have to do now is multiply both sides by 4. So the absolute value of x plus 3 is less than 4. This tells me that my centering point is at -3. X equals -3. And my radius of convergence is 4. I'm getting that from right here. So later on, we will look at how to find the interval of convergence, and that might give you a little better explanation as to why that's the radius. But for now, we're just going to identify that as being the radius of convergence for this particular power series. So when you come to class, we'll continue to work through these. I'll see you then.